चलो आज हम शुरू करती है चैप्टर 2 है development of Schrodinger wave equation. There are two types. One of them is time dependent Schrodinger equation and another is a time independent Schrodinger wave equations. Let's talk about the time dependent Schrodinger wave equations. Okay, let's see here. Consider a particle of mass m. This is a particle of mass m traveling along the x-axis. This is the x-axis along with momentum. This is the mass m and this is moving, so here is a momentum p about x-axis, px equal to mvx, where vx is a velocity along the x-axis, and associated with the particle. Already we discussed about this is the particle. Here is not mentioned about the associated with the particle. The moving particle is, this is a moving particle. This is a moving because it is traveling along the x-axis, is represented by the wave packet of the form. This is the most important point line. This is the most important point line. What is this? This is a moving particle is represented by a wave packet of the form. This is a psi of x comma t equal to a e exponential co power I kx minus omega t, where a is amplitudes and k equal to 2 pi by lambda is a, what is the k is the wave number, so it is a 2 pi by lambda. K is a wave number and this is equal to px by h cut. We know that k equal to 2 pi by lambda, and what is this? Another is a k equal to px by h cut. Px by h cut. Here we write px because of it is along the x-axis, so there is a px, and next is a omega. We need to put the values of omega, so omega equal to e by h cut because equal to, we know that equal to h cut omega. From this we can write the omega equal to e by h cut. This is the angular frequency, and then E equal to, this E is a total energy of the particle. What is the total energy? Total energy of any particle is the sum of kinetic energy and the potential energy. And this, substituting the values of this, what is this? K, we put the values of k, px by h cut and omega equal to e by h cut. This is an equation 1, and then we can differentiate equation 2. And this is the, first of all, this is equation 1, then another is equation 2. This is differentiating along the, we need to develop the time dependent Schrodinger wave equation. First we differentiated about the position x at 1 times, and the equation 1 is again differentiating with respect to time at 2 times. Let's see here what is going on here. And then the substituting the values of these k and omega from here, omega and k, and this equation becomes this, and the differentiating equation 2 with respect to x, so we get equation 2 के differentiate करो तो क्या होती है? इसके पास है we respect about the x-axis, so we can differentiating about the x-axis. X-axis, here is x, px into x, so we only differentiating about this. It is a partial differentiation methods. So this is the, first of all we differentiated about the base as a whole functions, so this is right as it is here, and the position is about the x-axis is this is the only x-axis. Here is a function of time, here is a function of position x, so we can differentiating the exponential power I px times x by h cut, so del x by del x is a cancel, so we can obtain only I px by h cut. and again differentiating about the equations, this equation 2 or this equation, we get this result. This is the same again, that this is the constant functions, no constant function, this is our functions, and this power differentiating method we write this is this may in this way, and the here is the only position function, is this is the only position function, and differentiating this and we get the double ipx by h card. So ipx by h card ko whole square, where I square equal to -1. There is, listen here, I write here I square equal to -1, so this is the minus this. Okay, next one is here. Next one is this is again accommodating or arranging this is in the this way, and we need to develop the time dependent Schrodinger wave equation. So we divide it both side by 2m and we get this. This is equation 3. We again differentiating equation 2 with respect to time, we need to develop the time dependent Schrodinger wave equation. So I differentiating the equation 2, this is equation 2 with respect to time. First of all, we differentiating about the position x, and the second time is we differentiating about the time t. So we need to differentiating about the time t. Time t is, here is the time t is a function of this, here is not a function of time. So first of all, this is and the same, we write this is same, and the time function, there is a time, so we need to differentiating about the time. Here is a I, here is a I, and e and t by h card. Okay, I e t by h card, here is a minus sign, this is comes here. So differentiating I e by h card and this, and we arranging this, finally we get this. Here is the psi of x comma t, here is a e is a total energy. It is a total energy in non-relativistic case. Since here is a most important point line, we write this. If you write this most important point line examination, you get the full marks. So since non-relativistic case, total energy, T means total energy, is the sum of kinetic energy and the potential energy. So equal to kinetic energy plus potential energy. Kinetic energy is a px square by 2m, and or kinetic energy equal to 1 by 2 mv square, and the potential energy is a general, it is only bx. We need to substituting the values of E from in the equation 4. So here is a psi of x comma t is attached with the E, so we multiplying this is by the psi of x comma t. So we multiplying this is both side by psi of x comma t, we get E psi of x comma t equal to px square by 2m psi x comma t plus bx and psi x comma t. And we have using equation 3, and here is a px square by 2m and psi of x comma t, here is in this. So we put the values of these from here in equation here, and we get this is equation 6. So equation 6 is the required one-dimensional time dependent Schrodinger equations. In three-dimensional of equation 6, we generalize this equation 6 in a three-dimensional. Here is a del x square is only one-dimensional, and we add the d square psi by dy square plus d square psi by dz square. We get the three-dimensional, and this is represented as a delta square. Delta square is a Laplacian operators or Cartesian operator. Here is a Cartesian coordinate system, it is just only the operators, so which is the required time dependent Schrodinger equation in the three-dimensional. And we here discuss this is the second order differential because it is as a order of 2 order, and linear equations, it is a linear equations, homogeneous equations, and partial differential equations. Thank you for watching my video. Subscribe for more detail. In the next class I discuss about the time independent Schrodinger equations. Thank you.